And with the understanding of different, wave bands and CCD chips and things, what's the future, 10, 100 years from now with telescopes?
Well, I would.
Or, for example, like the mirrors you described, being able to make these amazing lightweight mirrors that are thermally responsive to the temperature.
Well, I wouldn't even attempt to do 100 years. But there's a couple big futures that are going on. They're very exciting. One is a project called LSST, Large Synoptic Survey Telescope. It's an 8-meter telescope. Okay, so that's coming. Now, it's 8-meter diameter mirror, but for those of you who are photographers, it's an f1.5 telescope. Its focal length is 12 meters, and its focal plane is about 3 billion pixels. This telescope will, let's put it this way, it basically takes a whole Google data center to just sort of process the data to get it off the telescope and into a database. This is really big scale computing applied to science. This thing will be able to survey the whole sky every few days. All the sky that's available to it in Chile, to be more accurate. So one thing we're going to get is extraordinary amounts of data at much higher rates. That's coming in 10 years. The 30-meter telescope, which is going on Mauna Kea, is 30 meters, which is, well, I don't know, maybe the width of this facility. Yeah. Maybe a little more, maybe a little less. We could pace it out. But that's a big telescope. And then the most exciting thing, and what I think is the real future of optical telescopy, is space. The Hubble has been so successful and so revolutionary, both in terms of the scientific results it's created and the public awareness and appreciation of astronomy. It's sort of like reawakened, I think, our natural astronomical curiosity as people around the world. So I would love to see far more NASA work being done in the space telescope area. I mean, there's no question getting out of the Earth's atmosphere is really important, primarily because we're busy polluting it with light and gunk of all sorts, and because it won't naturally pass a whole bunch of wavelengths. So if you're out in space, you can then really go to town, really covering the whole wavelength range in a consistent way. So that's really the future, which means astronomy is going to be even more engineering intensive in the future than it has been in the past.
Okay, I think we have another one over here.
Will the project be able to do like regular scans for near-Earth orbiting asteroids?
Okay, will we be able to do essentially NEO work? NEO is the way it's normally said in the business, near-Earth objects. The answer is yes. With a 1-meter telescope, we can get down to fairly small objects. You wouldn't want one of these objects to fall around here. It would take out the whole valley. But we can get down to that level. But the problem with NEO searches is, well, if you're searching, there's no point in us doing it. There are better telescopes to find them. Where we would come into play is looking at objects and recording them many nights in a row to refine their orbits. And again, the bigger telescopes, when they're doing their surveys, if the orbit happens to be where the bigger telescope is looking, it's going to get the data, so we don't have to do that. But some of these guys go off this way, and they're scanning this way. And some of the ones, the NEOs that are wilder in their orbits, are the ones that have more risk. And so yes, one of our programs is going to be doing NEO tracking. And we intend that to be a program we're going to put together, and it's going to be almost entirely run by the learners. In other words, we'll let the learners, that'll be one of their things, is they can go adopt a NEO and develop an orbit for it.
Yeah.
And we'll make sure that the calculations are right, but have somebody really care about it.
As basically an astronomy educator, I was very much impressed by the amount of time and effort that you're giving this whole thing to the learner as well as to the scientists, and you have a whole education team, as you pointed out, and working on projects and developing things for the learners to do. And I think that's a wonderful way to do a project. It also gets you an awful lot of people looking, and it gets them doing some real science.
Right, and it's a myth. High school kids who are motivated, certainly anyone in junior colleges or smaller colleges, they can do science and write scientific papers as well as anybody.
Right,
So there's plenty of work to do.
right.
And I just think that's like a win for everybody.
Exactly, it's a
Real
win-win
work,
situation.
real science, real learning, and papers coming out the end with first authors from high schools and junior colleges is called very excellent.
That's great. Yes.
My question was, are you only interested in bringing these telescopes to students all over the world, or are you interested in bringing student engineers onto your project, like maintaining telescopes and computer science for the writing of the programs and all that?
Okay, the question is, are we interested in essentially having people come in? There's two answers to that. We're fairly full up with full-time staff. We're at the peak of the project, and there's a well-known rule in software engineering. If you add people to a project beyond a certain state, you only delay it. It's a proven scientific fact, I might add. And the magic size is about 8. The ninth person is probably a net negative most of the time in a computer science project. But the serious answer is we have an intern program, and we generally have at any given time at LCO 6 to 8 interns. And if any of you are interested, just get me the resume, send it into our job site. We look at everything, and we have had interns from Dos Pueblos High School, from their engineering academy, who've then been with us now 2 or 3 summers. Some of them have gone on to UCSB and other colleges around here, and then they still intern with us 10 hours a week. And intern jobs at LCO are extremely cool because we don't attach you to an engineer so you get to do their dirty work. We give interns actual projects. And most of our interns either work with themselves or with one other intern, sometimes with one of our staff, but they end up accomplishing a project. So that's how we like to do that.
Yes.
Oh, yeah, you mentioned earlier about the space, I mean, the satellites and getting the telescope images. Well, essentially, like, I guess Hubble is basically like a single lens telescope in space. And I don't know if you much about this. I heard it like maybe about 5 years back, but I think JPL was working on putting together like 2 separate lenses spaced far apart. Very, like, I guess they could control the length of what they're spaced, and then have those rotate around in space, and then take that image. So instead of just having, say, you know, a fixed number of meters the size of the lens, you could essentially make them much larger and still be able to project into space, because you're really only projecting just 2 small things instead of something really large.
Right. Yeah, exactly. That what you're referring to is essentially a concept of an interferometer. You have a mirror here and you have a mirror here, and when you combine the light, it interferes in very clever ways, and it's very nasty to unthread the signal, but it's a matter of computing. If you do that, what you get is the impact of having a 100-meter mirror, because these 2 mirrors are 100 meters apart, or 1,000 meters apart. You have a 1,000-meter mirror apart. Well, then you can begin to see structure and sunspots on external stars and things like that. And so the interferometric technique allows you to get extremely high resolution. It's only practical in space because you don't have all the atmospheric stuff to deal with. And so that is